and welcome to Coding TensorFlow. I'm Karmel Allison, and I'm here to guide you through a scenario using TensorFlow's high-level APIs. This video is the third and final part of a three-part series. In the first video, we looked at data and how to prepare your data for machine learning. We then moved on to optimizing your data for machine learning with TensorFlow and Keras, including building a simple model. And here's the model we defined. We will start with a simple sequential model, which strings together the modular Keras layers, hooking the output of each into the input of the next. Our first layer will do all of the data transformations we just discussed, and then we go through some standard densely connected layers. Our final layer here will output the class predictions for each of the 4 wilderness areas that we are interested in. Notice here that we are just establishing the architecture of our model, and we still haven't yet hooked it up to any data. Once we have the layer architecture established, we can compile the model, which adds the optimizer, loss, and metrics we are interested in. TensorFlow provides a number of optimizers and loss choices, which we could explore if we wanted to. And finally, the rubber meets the road. We pass our dataset into our model, and we train. Now, in a real-world situation with large datasets, we would likely want to leverage hardware accelerators like GPUs or TPUs, and we may even want to distribute training across multiple GPUs or nodes. You can find out more about using distribution strategies for this in the links included in the description below. So for now, I will just point out that this same code will work in the distributed settings and when eager execution is disabled. For now, we will just assume that we will wait for this to finish training. Once it's done training, you can test it, and while that's pretty straightforward, we first need to load in our validation data. It's important here that we use the same processing procedure for our test data that we did for our training data, so maybe we'll define a function that we can use in both cases to ensure repeatability. We call the evaluate method of our model with the validation data, which returns the loss and accuracy that we get on our test data. Note here that because we took care of our data transformations using feature columns, we know that the transformation of our input validation data will happen in the same way as it did for our training data, which is critical to ensuring repeatable results. So now we've validated our model on independent, held-out data that was processed in the same way as our training data. And we can pretend for a minute that we are happy with the results and we are ready to deploy this model. There is a lot of tooling that is required for real-world deployment, which the library TFX makes possible. I've put a link to this in the description below. TensorFlow provides a model saving format that works with the suite of TensorFlow products, including TensorFlow Serving and TensorFlow.js. The TensorFlow saved model includes a checkpoint with all of the weights and variables, and it also includes the graph that we built for training, evaluating, and predicting. Keras now natively exports to TensorFlow saved model format for serving. This saved model is a fully contained serialization of your model, so you can load it back into Python later if you want to retrain or reuse your model. And now we've gone through all of the critical stages to build a model for our data in TensorFlow. And maybe we're done. It could be that this is the perfect model and we're happy. But then we'd all have to go and find new jobs, so let's assume that we want to improve the accuracy of the model we have built. There are lots of places we might decide to make changes. We could go and collect more data. We could change the way we process and parse the data. We could change the model architecture, add or remove layers. We could change the optimizer or the loss. We could try different hyperparameters, and so on. What I will show you today is how to use the same data and features to try out one of TensorFlow's canned estimators, which are built-in implementations of some more complex models, including those that don't fit nicely into a layer-based architecture. So what if we wanted to shake things up and try a different model? To rewind, this is the model we had, a densely connected neural network. Let's try changing it. Here, we are using the same feature columns, but we're configuring one of the TensorFlow canned estimators. We are using the DNN linear combined classifier, which is also known as the wide and deep model. And that gives us an architecture that looks something like this, allowing us to trivially leverage all the research that went into developing this model structure. This model combines traditional linear learning with deep learning, and so we can feed in our categorical data directly to the linear half, and then configure a DNN with 2 dense layers for the numerical data. We can then train the wide and deep model just as we did with our other model. Notice here that the canned estimator expects the input function rather than the dataset directly. Estimators control their own sessions and graphs, so that at the time of distribution, they can build and replicate graphs as necessary. So our input function here gives the estimator the instructions for getting our data set and producing the tensors that we want. And the estimator will then call this function in its own graph and session when necessary. Here, we wrap the same data loading function that we used in our previous model in a lambda with the correct file names pre-configured so that the estimator can call this function at runtime to get the appropriate features and labels. We can use the same strategy to evaluate using test data. And lo and behold, if we run this for 20 epochs, we have another trained model that we can compare to the first. Note that this is just one of a number of canned estimators that TensorFlow offers. We have boosted trees, model for time series analysis, RNNs, walls, and more as well. Note that for estimators, we first have to tell the model what shape and type of tensor to expect at inference time. For that, we have to define an input receiver function. It sounds confusing, and I'm not going to lie, it's a little confusing. We want a function that builds the tensor shapes that we expect at serving time. Luckily, we can use this convenience function, which just needs the shapes of the tensors we will want to run inference on. Because we are in eager mode, we can just grab a row from our dataset and use that to tell the convenience function what to expect. Here, we grab the features from the first row and don't do any additional processing, because we are assuming at inference time the data will look the same, just without labels. In real-world scenarios, your inference data may need additional processing, such as parsing from a live request string, and the input receiver function is where you would encode that logic. We can then use the function returned by build raw serving input receiver function to generate a saved model that can be used in TF serving, TF hub, and elsewhere, just as we did with Keras. So now we've made a full loop, and if we had more time, we could keep going and try out some more of these paths. I'll leave you to explore that, and I hope that this series has been as fun for you as it was for me. Remember, if you have any questions, please leave them in the comments below, and don't forget to hit that subscribe button.